This is the introduction to electricity and electricity markets. So in this first lecture, we will just introduce electricity and some of the key characteristics of the electricity market. There's four segments of the electricity industry. There's generation, that's the conversion of fossil fuels or nuclear fuel, running water, wind or solar, into energy, electrical energy. Then there's transmission. So we take the electricity that's produced by the generators and we transmit it over high voltage transmission lines, and then that's transmitted to distribution networks where the voltage is ramped down. It's transmitted at high voltage so that it reduces losses. It's more efficient to transmit at high voltage, and then distributed to households and commercial businesses and industries at low voltage. Then there's retailing. It's the sale of electricity to final consumers, billing users, collecting payment, financial contracts with generators. Here's an image of the segments. So we have a generating station that's going to be coal, nuclear, natural gas, etc. Then that electricity's the voltage is ramped up, and then it's transmitted over long distance transmission lines at high voltage, and then it goes to a substation for step down or reducing the voltage, and then that's where it's distributed to the customers, the retail customers. There's some special characteristics of the electricity industry. First, demand must equal supply at all times. There's no storage of electricity. That's number two. Storage of electricity is very difficult. So that means that there's this kind of bathtub on the electricity network, and sort of like the oil bathtub, except in this case, the bathtub level cannot fluctuate. Demand must equal supply at all times. We can't have less supply than demand, or we would have a blackout. We can't have more supply than demand, or that electricity would have to be grounded somehow. Number three, generation of electricity is subject to severe capacity constraints. So generators can't produce more than their rated capacity. If you have a coal plant that's rated to produce 1,000 megawatts, it can't produce 1,500 megawatts. Number four, real-time demand for electricity is extremely inelastic. And that's because households and commercial businesses do not see price changes. So if the price doesn't change, you can imagine demand is inelastic. You have no incentive to change your consumption. You just turn on your light bulb whenever you feel like it. You put laundry in whenever you feel like it, because you don't see price changes at different times of the day or different times of the month. Number five, electricity must be delivered through a transmission network that is also subject to capacity constraints. So those large, long-distance transmission lines have capacity limits on them as well, and you can't just shove more electricity through them. Same with the distribution network. Most of these issues would be dealt with if number two was fixed, the storage of electricity. If we could store electricity, we wouldn't have nearly the problems we do. So number one, demand must equal supply at all times. Let's look a little more into this. Demand must equal supply at every second at every location on the transmission network. The grids are regional, sometimes covering many states, and so the demand in every state and every household has to be met by equal supply at every second of every day. This is a huge problem to solve at every second. Large fluctuations in demand during the day. There are large fluctuations in demand during the day, even within each hour. So you can imagine when is the peak demand? Well, it's going to be around 5 o'clock when everybody gets home and turns on their lights and turns on their stoves and starts cooking dinner. There's also large fluctuations in demand over the course of the year. So in places where it's hot and people use AC, then the demand is highest in the the summers when they need to crank up their AC. And then especially highest during the hottest afternoons in the summers. We also need to be concerned about unplanned breakdowns of generation units. So sometimes you have a coal plant that just shuts down. They need to shut down for an emergency or something. And so there has to be sufficient backup supply in order to meet the demand despite unplanned breakdowns. This requires central coordination by a system operator. So you have an entity that we will get into later that's actually equates supply and demand in real time. It's called an independent system operator, or an ISO. There's second by second balancing of supply and demand and provision of backup generation on standby. And there are separate services with their own markets called ancillary services. So this is a huge market process that happens on a second by second basis. There's supply bids that we will talk about being bid every second from generators. Information only flows from households to generators, not vice versa. This is a real problem for the generators. And what do I mean by this? Information is flowing in the form of demand, right? So when you flip your light switch on, that's a piece of information flowing to the ISO or the generators. The ISO is the coordinator of the grid. There's no information flowing to your household like prices. So you basically exist in this bubble when you're in your house, and a commercial, the businesses do as well. They just consume electricity with no information coming from the generators, except, of course, in the form of a monthly electricity bill. So here's a picture of what it looks like inside of the ISO. Here, these people are equating demand and supply in real time. Number two was electricity storage is very expensive and rare. So this is the future of electricity. We're getting to the point where we can have some large batteries. We of course have batteries in our homes and in our cars and stuff, but we don't have grid level electricity storage yet, at least in large scale. Tesla is working on this, as are other companies. And once this gets solved, once the cost of storage comes down enough where many different utilities are purchasing storage, then a lot of the problems we will talk about in this section of the class will be solved. So here's an example of one of those storage units. There's a 20 megawatt battery in Ontario, California, opened in 2017. You can read about that on the news if you'd like. Here's one of the major problems in electricity markets today. We want to have more wind and solar or renewables on our grids. But the problem is that wind and solar are what's known as intermittent forms of generation. What do we mean by that? So the wind doesn't blow all the time and the sun doesn't shine all the time. Of course, the sun doesn't shine at night, but what happens when clouds come over? It means that there's less electricity being produced by the solar panels. And what happens when the wind stops blowing? It means there's no electricity being produced by the wind farms. And so this shortfall in supply needs to be met by supply from somewhere else, and that's typically natural gas producers. And it's easy to deal with when the fraction of renewables supplying a grid is fairly low, maybe 5% of the supply is from renewables. But as that percentage increases, it becomes harder and harder to deal with. So imagine if 50% of your supply is coming from renewables, and then maybe solar, and then some clouds come over, and then all of a sudden 50% of your supply is gone. You need to have some backup capacity waiting in order to meet that additional demand. Number three was generation is subject to severe capacity constraints. Each generation plant, the coal plants, the natural gas plants, have a nameplate capacity. The marginal cost of generation rises very steeply around the nameplate capacity. So as the plants reach their capacity, their marginal costs rise dramatically. The marginal costs are basically flat until they reach their capacity. Producing more than the nameplate capacity for extended periods of time can significantly increase the risk of failure. So if you produce, a coal plant can push a little more than their capacity, but doing so could cause them to shut down. Number 4, real-time demand for electricity is extremely inelastic. The final price charged to most end users is constant and does not depend on the real-time price. The real-time price is the wholesale market price, the ones that the generators are being given. So despite the fact that the wholesale price is fluctuating, retail consumers see a fixed price. So this provides no incentives for consumers to reduce consumption during high demand periods like the peak hours, 5 p.m., or during the summer months. There are real-time meters being installed in homes, but to date, only major industrial users face real-time prices. We haven't gotten to the point where households face real-time prices yet. Number 5 was electricity delivered by capacity-constrained transmission network. So electricity generation and demand load are usually in different locations. We don't have power plants right next to our households. Instead, we have power plants, at least in Fort Collins, maybe 10 to 15 miles north of Fort Collins. And we need to get that electricity to the household, so we need transmission lines. And these transmission lines are subject to capacity constraints as well, which can lead to different prices in different regions. Right? If you have a capacity constraint on a transmission line, the price at the end of that transmission line is going to go up because supply is limited. The image here really shows how prices change based on capacity constraints on the transmission network. So these are the prices for electricity at different region or different parts of the East Coast during heat waves. You can see as you get closer to the East Coast where all the population centers are, the prices are going up. The red is higher priced and the blue is lower priced. And this is due entirely to capacity constraints on the transmission network. So that was the introduction to electricity markets. We will cover a lot of this in more detail in the subsequent lectures.